some house cleaning out of the way and let them get settled in. First off, good afternoon. My name is Jason Thomas. I'm a project engineer at America Makes, and I'll be your host for today's America Makes TRX webinar series. Just a little background on the TRX webinar series before I introduce our speakers. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium called the America Makes Technical Review and Exchange webinar series was created. By creating this platform, it allows the additive manufacturing and 3D printing communities to come together and share knowledge and experience with the broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can contact the America Makes TRX webinar series administrator, Jason Thomas, directly. A few important notes before we kick off the series. At the end of the presentation today, there will be an opportunity for a brief question and answer. If during the presentation you do have a question, please submit it in the Q&A space. Screen. Like I said, I'll do my best to get to all the questions. So today's webinar is on an emerging technology, liquid metal jetting. Key takeaways of today's webinar are to be for you to learn firsthand how Lawrence Livermore is pushing the limits of droplet on demand and where they see potential for the technology. Discover current applications for 3D printed aluminum alloys. Explore how this highly deployable industrial metal 3D printing technology can provide solutions for the shop floor and supply chain challenges. And review development plans for future capabilities, specifically regarding materials. Now, without further ado, it is my pleasure to introduce Tim Schniepp from Xerox, and joining him from Lawrence Livermore National Labs is Nick Watkins, Kellen Trexel.
Thank you for the introduction. I appreciate it.
Nick Watkins.
Oh, you're cutting out just a little bit, Jason. So if you don't mind, I'll take it from here. I appreciate the introduction. Yeah, as mentioned, my name is Tim Schniepp, and I lead the application engineering team here at Xerox. My background is actually in aerospace manufacturing primarily. I started my career at Lockheed Martin, spent some time at GE Aviation, and then a couple other places as well before getting into additive manufacturing a dozen or so years ago, first as a user of the technology, a customer, and then spent some time at Stratasys and 3M, and now here at Xerox as well. And it's my pleasure to be joined by the Lawrence Livermore team. A couple of them are here representing their jetting AM group. Victor is unable to make it, but Nick and Kellen, you're in good hands with them, and they'll share a bit more about the research they're doing on metal jetting. I'm going to go ahead and turn off my camera for my presentation, primarily because I have a cold, and I might have to use a Kleenex here or two, here and there. So bear with me on that note. But I'm excited to be here to talk about our technology. So we call at Xerox the group in which we are focused on additive manufacturing is known as LM Additive. This is a recently formed entity, but this is our name now. And the technology that we have developed is called ElemX Liquid Metal Jetting, LMJ, or Liquid Metal Additive Manufacturing. For a little bit of history, this is a technology that was invented by a small startup called Vader Systems, and Xerox acquired this technology in 2018, and then we've been working to commercialize it, advance and commercialize it since that time. We launched officially early last year with the U.S. Navy as our launch customer, and I'll talk a little bit more about that relationship. But overall, my plan here today is to give you an overview of how the tech works, share a little bit of performance data, some mechanical data, and then talk a little bit about applications before handing it off to the Livermore team to discuss their research additionally. And also, as you can see here in the images, we also recently launched, the LM Additive team launched a digital manufacturing platform that we call LM Navigator. And I won't talk a lot about that today, but if you're interested in learning more about it, please don't hesitate to follow up with me. It's really geared towards helping engineers assess printability of a given part and then make financial business case-based decisions. So essentially helping you determine, can I print it, upload a CAD file, have the system and analyze whether or not it's printable, and not just on Xerox technology, on any available AM technology. And then it provides a wealth of information to help you decide if it makes sense from a business perspective to do so. So happy to talk more about that in the future as well. But today's focused on the additive manufacturing technology LMX. So our view overall of AM is that it's well established for the value that it provides, both from a design freedom perspective and in product development, through to addressing supply chain issues. But that said, while there are a lot of great metal AM technologies on the market, those incumbent technologies tend to come with some challenges. Most tend to be powder-based. While a great capability and great technologies, that comes with some challenges, primarily in handling powder and implementing those technologies in the factory. They tend to require some significant facility modifications and investment in able to safely handle those materials. Our LMX platform, on the other hand, is a wire-fed system, so it inherently addresses a lot of those challenges. And as a result, we're able to produce parts very quickly, and it really is a simpler and easier approach to metal AM. And so I'll talk a little bit more about how that works. Here's just a quick high-level view of how the system is configured. And I also have a couple of videos that I'll show you as well here in just a moment. The videos, or the one video in particular, as well as this image, are from what we call one of our engineering rigs, or engineering systems, where we do our development work. The primary difference is just that they don't have the external skins, so you can see everything a little bit better. So that's why we show that. But in here, fundamentally they work the same as our production machine. So you can see here, it starts with a spool of aluminum welding wire, aluminum wire, and then analogous to an FDM polymer AM system, that wire feeds up into a heated head. We melt the material with resistance heaters. It's held in a molten state in a little ceramic crucible within the head. And we use electromagnetic jetting to dispense a continuous series of droplets onto a heated build plate. So you see that here. And I'll show you a video here in just a moment that gives you an idea kind of how that works now. So this is first of two videos that I'll show. This is a rendering that basically illustrates what I just described. So let me go ahead and see if this will play. Yes, wonderful. Hopefully you can all see that just fine. So again, this will be a little bit of replication of what I just described, but excuse me, there you see the welding wire, the spool of wire. It's a 20-pound spool, pretty standard material. So, easy to handle, easy to use, easy to store. That feeds up into a heated head where resistance heaters melt it into the little ceramic crucible that you see there. That's about 4 milliliters in volume. We flood that with argon gas that provides a shroud to help control and reduce oxidation. And then there's a set of coils that you see there that we fire continuously at high frequency, and that creates a Lorentz force, which dispenses the droplets onto the heated build plate. As you can see, we move the build plate in the XY direction. The head is kept stationary, though it does go up and down in the Z direction, and we do that to help improve repeatability and gives the system additional stability. And then all industrial controls, we have a partnership with Siemens on the hardware side that leverages their best-in-class controllers and gives us some excellent manufacturing-oriented capabilities. Here's a static view of essentially the same information, and we're happy to provide a copy of this presentation afterwards for reference. So, but the videos are obviously fairly large and difficult to share, but can send out a copy to anyone who would like that. Just feel free to email me or the American Makes team, and we'll get you a copy, and then you'll have this information. But essentially, it just summarizes what was shown in the video. So our view then on the benefits of the technology are shown here. First of all, particularly when looking at the total cost of ownership, this is a very cost-effective technology. We use the wire feedstock, which is inherently much more cost-effective than using custom metal powders, as well as the cost aspect. Then is also the significant safety advantages. Unlike both laser powder bed fusion or binder jetting, there's no real special facility modifications required to handle those powders. So it's a much easier technology to implement. There's no inherent explosion or health concerns associated with it. And I'll show a video of a part being made here in just a moment. And then along with that, the cycle time, the time to produce parts is very fast. This technology at this stage is really best suited to small to moderate size parts. If you think of it as a supplementation to casting, that's where we tend to, or our customers tend to have the most success in the industrial spaces, is when they use it to supplement casting supply chains. Though it's not limited to just that, of course, but without the arduous post-processing associated with some of the powder-based technologies, it's a much faster time to part, which you'll see here in just a moment. And then finally, I'll share a little bit of the mechanical data or physical mechanical data here in just a moment. But essentially, the performance matches the requirements for forecasting, so it can be viewed as a drop-in replacement in many cases, and delivers really good performance overall. So I'm going to show you a second video here. This is of a time lapse of a part being made. Hopefully you can all see that just fine. So what you see here is a small part being produced. You can see there's actually an offset between the jetting nozzle and the part. It's a non-contact method. You can see the build plate, the heated build plate moving there. This part took just over an hour to build. It's a couple inches tall for reference. And again, this is on one of our engineering rigs. So you're going to see the extent of post-processing here in a moment, and there's just slight differences between this and the production machine. The first of which is there's that small build plate that sits on the main build plate. And we just do that for handling purposes. So the operator comes in here with simple hand tools, takes that hot build plate, goes in a very sophisticated bucket. So that's just room temperature water, and it's a thermal expansion difference between the part and the build plate that creates that separation. And while that was picked up with a hand tool, you could literally just reach in there and grab it if you didn't mind getting wet. You can have that part in hand literally in seconds. As you can see, the surface finish is equivalent to that of casting as well. It is somewhat rough. So for some applications, there will be some post-processing required to machine critical interfaces or some features, drill out holes, all those kind of standard aspects that would be associated with either casting or other metal AM technology. But overall, the time to part here, as you saw, is very, very fast. I'll talk a little bit about the mechanical data here in just a second. That's where we would recommend a heat treatment as well. The as printed material properties, the material is in a relatively soft state, so the strength is considerably reduced compared to that of a heat treated sample. However, the elongation obviously is much higher as it's very soft and ductile in that stage. But for many applications, it can be used as is. So that if you have custom fixtures, some replacement parts and those types of things where mechanical performance isn't the only driver, it can be used directly off the printer. And then, excuse me, shown here is a summary of the high-level specs for the machine itself. And then you see in the image there, that is also essentially the production machine. So when you invest in the ElemX, everything you see there is provided. So, very much a turnkey solution. You see the printer in the center. On the left-hand side in that image, there's a small chiller. That's what regulates the temperature of the head. Keeping in mind, again, that the head and the bed are heated. The build chamber itself is just passively heated at this stage. So we are adding active thermal controls to the second version of this printer. And those types of changes will be retrofittable. And that becomes relevant in just a moment. I'll talk about that. And then on the right-hand side in that image, you see the build plate removal cart. So in the video I showed, it was an operator with the simple hand tools removing the small build plate. In a production setting, we provide this cart that comes in, takes that larger hot build plate out of the printer, and then you use a little crane or lifting device to transfer that into a water bath. So it's still pretty simple and straightforward overall, and there's plenty of opportunity for automation in this process as well, and that's something we're working on also. And then on the right-hand side of the slide are the specifications. So the build chamber itself is 300 by 300 by 300 millimeters, about 12 by 12 by 12 inches. Though we do at this stage recommend a slightly lower Z height. And the reason for that is it does depend a little bit on part geometry, but we rely on heat transfer from that hot build plate into the part to keep the part surface, the build surface, at the optimum temperature. And we found after that 4 to 6 inch range that because aluminum transfers heat so well, it cools down relatively quickly and we don't get as good of droplet adhesion, and we start to see some variability in mechanical performance at that point. And it does depend a little bit on geometry. We have built parts taller than 160 millimeters successfully as well, but that can vary. But I did mention we're adding thermal controls to the chamber itself. It's going to be an actively heated chamber, and that's what will extend that build size up to the full build volume. So that's coming later this year, and as I mentioned, that's a retrofittable change. So we try to take that approach from a development perspective, and that any updates and enhancements we do over time, which is a pretty rapid rate, we can then incorporate into existing printers that are already in the field. And then the rest of the specifications are kind of shown there as well. And like I said, I'm happy to provide a copy of this for reference. Shown here is a summary of the basic physical and mechanical properties, as I mentioned. So I talked a little bit about it already, but the surface finish is equivalent to a sand casting. Tends to be right around 28 to 30 micrometers. RA is the average surface roughness. It does vary a little bit relative to build orientation, the surface relative to the build orientation. So downward facing surfaces, for instance, tend to be a little bit rougher than a top flat surface. We do have quite a bit of data, characterization data on surface finish that we can provide upon request as well. That's no problem. And then we routinely get densities greater than 99%, even 99.5% on the printed parts. And there's no HIP process or those types of post-processing are not required to achieve these densities. We did some evaluation of those types of approaches and it didn't see much improvement at all. So it's not something we recommend or require. Some porosity is inherent to this process. So if you picture the jetting process, the droplets of metal come out, or molten aluminum come out as spherical in nature. It's a 500 micron orifice that's used for the jetting. So they have that half millimeter diameter. And then as they land on the build plate or the subsequent build layer, they flatten out a bit, take on a disc-like profile or a pancake-like shape. So they end up being about 1/4 millimeter thick, about 0.6 to 0.7, around 0.7 millimeters in width usually, or diameter. And as you stack those little pancakes on top of each other, as you create your build paths, you do occasionally trap in some small voids or small pores. So they tend to be 250 microns in size or smaller, typically even smaller than that, and then distributed along those droplet boundaries. But some porosity is inherent, though it is quite low. And we do have plenty of microscopy work that we can share as well. Around characterization of density and the nature of that porosity. And then the bottom table shows basic mechanical performance after the T6 heat treatment that I mentioned. So that's a printed block that then heat treated to the T6 condition and the specimens are machined. In the first column of that table is the specification requirements for casting. A356 has the same composition as the 4008 series alloy that we offer. So as you can see, the tensile strength, both yield and ultimate, not only meet the specification requirements, but are pretty isotropic in performance overall. Some anisotropy does start to show up in elongation at break, still well above the spec limits there. Ductile failures, so which is always a positive. But some degree of anisotropy shows up, and we attribute that to some natural greater variability in the Z direction, both in the surface profiles, as well as we get a thin oxide layer that builds up during printing, even though we flood the head and with argon gas that provides a shroud and follows the droplets all the way down to the build plate. You still do get some oxide buildup. It's very thin. Some materials like the 4008 series alloy that we offer now is pretty tolerant of that. Others can be more sensitive. So we have a number of different aluminum alloys in development. And we're working through the optimization of print parameters to optimize mechanical performance for those two. The next material that we will be making available is 6061, which obviously is a pretty ubiquitous aluminum alloy used very broadly, high strength alloy. and that'll be coming out later this year as well, along with that heated enclosure that I already talked about. So shifting gears just a little bit here from performance to applications, just a couple more slides, talk about kind of where some of our early customers are implementing the technology today. So from our view and what we found with customers is, it's pretty versatile. So used everywhere from for product development and prototyping all the way through to various custom jigs and fixtures and process aids. That's a very common, as you likely all know, a very common application for polymer AM as well. This technology fits in there very well also. It's a technology that can be deployed easily on the manufacturing floor. And I mean, for comparison, we have it in an office building in our facility in Raleigh, North Carolina, which you're all welcome to visit at any time. But because it is a safe and relatively easy to use technology, it's also very easy to implement. And so it has a lot of common application spaces as polymer AM, but now you can use metal parts, so a little bit more durable for tooling and things like that. And then of course, production parts are where people focus, where it has the most impact. And given the throughput, the typical throughput and size and type of parts that are suited to this technology, it tends to make the most sense for like spare parts and replacements, or to supplement existing supply chains, like I mentioned. So we have a number of industrial customers that, particularly over the past couple of years with the pandemic and all the ongoing supply chain issues around the world, have had shortages and line shortages and issues with existing supply chains for their cast parts. So we've worked with them to qualify the ElemX, gone through the PPAP process in some cases for heavy equipment provider, for example, to qualify it to produce spare parts to keep those manufacturing lines up and running. So really good use case for it. A couple more slides here. As I mentioned, we kicked off our relationship, our commercialization of the technology with the U.S. Navy as our launch customer. We do have a formal CRADA with them, a cooperative research and development agreement, really focused on characterization of the technology, geared towards identifying applications for the Navy. They have obviously their goal around the floating factory and getting AM technologies on board a ship, so that they can produce spare and replacement parts on demand to keep ships up and running, and they don't have to stock so many parts and keep an inventory, all those types of challenges, obviously. But to date, the higher performing metal AM technologies available are all powder based, and they are obviously very reluctant to put powder based technology on a ship because of the associated safety concerns. So ElemX addresses those very well, and they happen to be very excited about the technology. Here are just a few of the early example parts and use cases that we worked on with the Navy team. Again, really geared towards spare parts and replacement parts on board ships. So on the left-hand side, the Navy actually hosted a broader crowdsourcing competition to address the issue with light fixtures on board ships. Apparently they fail due to the vibration environment, and they're a huge maintenance nuisance. It's not a super exciting use case necessarily, but it's a legitimate maintenance problem, and AM can help address that. And this was the Naval Postgraduate School's submission for that. I should have mentioned that the NPS, Naval Postgraduate School, is where the partnership printer was implemented initially. So that's our point of contact into the Navy. And then the subsequent two images there are similar in nature. A couple spanner wrenches and valve handles. These are items on board ships that are safety critical and absolutely necessary, and are all over ships in a wide range of sizes for the various customized to the various applications. And so the ability to print such parts on demand when needed, when they get broken, damaged, lost, etc., is very valuable to the Navy. A couple more here. First, because aluminum does transfer heat so well, we get a lot of interest for various heat transfer applications. So these are heat exchanger and heat sink example parts that we've worked on with various customers as well. And then finally, a wide range of different pump housings and nozzles and mechanical components. So on the left-hand side is a part of a roller pump assembly. this is a Xerox design part based on the customer part that I mentioned, where we went through the PPAP process, so it was sort of a similar application. But we weren't obviously allowed to share that exactly, so this is our version of it. And then in the middle there, just a bracket, a mechanical assembly component, and finally a distribution nozzle on the right-hand side. All of which we can share more information on upon request. So with that, I appreciate your time. Hopefully I helped explain how the technology works a little bit better. We are very committed to helping implement this technology however we can, whether that's technical validation and leveraging being such a large company with global experience that has a lot of advantages, and we bring that to the AM space. So if you're interested in learning more, please don't hesitate to reach out to me. And here's my email address. And like I said, happy to provide this and happy to share more. So with that, I will hand things over to the Lawrence Livermore team, starting with Callan. So bear with me just a second while I give him privileges. There we go. Are you there, Callan?
Yeah. Can you hear me?
Yep.
My apologies. I'm pulling up the slides. Let's see.
I'm just happy I made it through the whole presentation without coughing or sneezing, so I must be trending in the right direction.
Yeah, my apologies. Little technical difficulty here.
Is it anything I can help with?
Let's see.
You go to the menu on top.
Yeah.
There's the third thing is share. I don't know if you're just not seeing it or if it's something
Yeah, I think it's more the PowerPoint itself that's kind
yeah. Okay.
of giving me some issues. All right, let's do this now. Okay, can you see?
Here we go. Yep.
Okay. Okay, I think we got it now.
You got it.
All right, awesome. Yeah, so thank you, Tim. My name is Kellen Traxel. I'm a postdoc at Lawrence Livermore National Lab. I've been here for about 10 months, working in the liquid metal jetting group. My background is more on the laser powder bed fusion side, directed energy deposition. So I definitely come to this liquid metal jetting technology from that perspective. And as you've seen, a lot of the advantages that Tim has shared have really taken notice from not just Lawrence Livermore, but kind of the whole national lab system. And so we have an LMX on site here that we've been working with since about November. And so our goal here, me and Nick Watkins, is to kind of share just a little bit about the lab and a lot of the research that our group has been doing, and some of the papers that have been published on sort of pneumatic based liquid metal jetting, and then to talk a little bit about our use of the LMX and what we're trying to accomplish. So let's see if, okay, did that slide advance, Tim?
Sorry, I was muted. Yep, you're doing just fine.
Awesome. Okay, great. Yeah, so the National Lab System, it really spans a spectrum of kind of fundamental science to applied technology. And on top of that, there's different labs that have sort of more single use, single purpose versus sort of multi-program, multi-purpose labs. And so we sit kind of on the applied technology side with Los Alamos and Sandia, which we work really closely with. And a lot of it is applied research. So the lab itself sits about, Livermore is around an hour outside of San Francisco, almost like directly east. We sit on about a 1 square mile, is upwards of 7,000 employees, and has been around for nearly 70 years now. So we have a good federal budget. We're operated, we're basically contracted through the Department of Energy. We also have a couple external test sites, and kind of a fun fact is that the Mythbusters actually did some explosive testing at our Tracy test site, which is a little outside of Livermore, maybe 15-20 minutes. So kind of a fun fact. Along the lines of what we do, like I kind of said, it's more on the applied technology side, but it spans everything from just the science and engineering, also a lot of computing. There's a lot of internally developed codes that are internationally recognized for their ability to do complex simulation and computation. And kind of the key things we work on are so-called stockpile stewardship, reducing weapons of mass destruction threats, working in reduction and deterrence through multiple domains, and then also a lot of energy and climate security thrusts. And sort of within all of that, you can find a space for manufacturing. And the lab has heavily invested in 3D printing technologies. I'd say in the last about 15 years, 10 to 15 years or so. And this building that we have built basically outside the fence, its purpose is to bring in industry and inspire collaboration with external companies that are doing exciting research in the 3D printing field. So if you're interested in some of the work we do, or perhaps you've seen other things that the lab has done with different technologies. Obviously we're just talking about liquid metal jetting today, but we have a lot of other partners that we work with in not just even metals, but polymer and ceramic 3D printing. So happy to work with industry partners and academia in that regard. Oops. I think there's a little delay here. Okay. Yeah, so sort of part of the reason I joined the lab, and what the lab has really been known for in terms of the metal 3D printing research is on the powder bed fusion side. And there's been a lot of research that colleagues have done on sort of beam shaping, looking at digital twins, and on top of that, doing really high fidelity simulations. So as I kind of mentioned, there's a lot of custom code and programs that have been developed here at the lab. And so these are great, but we're also looking at sort of these more emerging and advanced technologies like liquid metal jetting, and have been for several years. And so while powder bed fusion is kind of on the forefront, the powder based methods, we have a legitimate interest in the jetting based manufacturing. And so with that, I'll pass over to Nick Watkins, and he'll talk about a little bit about that research. And just let me know, Nick, when to move slides.
Sure. Can you hear me?
Yeah.
Okay, great. Yeah, my name is Nick Watkins. I'm a staff scientist here at the lab. I've been here about 6 years, and primarily I do more biomedical applications and microfluidics, but about four or 5 years ago, I was tapped on to start this internal project with internal funding to initiate liquid metal jetting, creating this capability here at the lab, and it's been growing, and our team is growing, and we're now partnering with Xerox, and now have, as already mentioned, ElemX, and we're doing a lot of great research with that. So first, I'm going to talk about some research we've done, which is primarily with the pneumatic system. So liquid metal jetting is a relatively new technology compared to powder bed fusion. You can say liquid metal jetting right now is where powder bed fusion was around 20 years ago. So why liquid metal jetting? There are benefits of liquid metal jetting over powder bed fusion, such as no powder, reduced feedstock, pre-processing, and minimal part post-processing. As a result, we are advancing liquid metal jetting science from the nozzle to the build plate. For example, in one study shown on the left half of the slide, we have looked at the effects of liquid metal jetting on the properties and structure of printed metal parts using a pneumatic printhead. And we found that the properties such as density and hardness of the printed part matched the feedstock very well. However, the microstructures were quite different. Feedstock had small equiax grains, while the printed part had large columnar grains that ran up through the build direction. Of interesting note was that we could not detect oxide within the tin part despite it being printed in air. Advancing liquid metal jetting science includes modeling in addition to experiments to better understand the jetting dynamics of various materials. In another study on the right hand of the slide, we compare experimental results of droplet breakup dynamics in the left figure to various models on the right. We found that accurately modeling liquid metal jetting has its challenges, but it does give us plenty of opportunities to advance in this area by adding additional physics to better capture the experimental results. Next slide. In a follow-on study, we looked further into better understanding the printability of liquid metals. I want to give a little background. By using aqueous inks of various properties, Liu and Derby from University of Manchester developed a droplet on demand printability window based on two dimensionless numbers, the jet Weber number and Z. The jet Weber number roughly relates to how strong a momentum pulse is applied to the fluid, and Z relates to fluid's surface tension and viscosity. Higher Z means the more likely the ejections will create unwanted satellites for a given jet Weber number, as shown in the downward trend of the window. These satellites may diminish part quality by reducing resolution and density. Notice how the window predicts that no satellite-free droplets could be printed beyond a Z of around 700. So we tested this limit using liquid metals because their unique characteristics place them in the high Z region, as shown by the orange circle. We performed an experimental sweep of Weber jet and Z using various molten metals to not only understand the optimal operating range for liquid metal jetting, but to also find the highest Z at which we could still print single droplets. Next slide. Okay, we found that not only can we print stable droplets at high Z, but at Z of over 3 times higher than the extreme corner of the printing window. So we essentially broke the window. We were able to print satellite-free droplets for all Z tested and found a stable operation range for Weber jet between 2 and 4 for all metals tested. The takeaway is that you can essentially jet any metals based on the fact that we were able to successfully jet pure germanium, which is the most difficult metal to jet. The video to the right shows the ejection of a satellite-free germanium droplet at a Z of around 2500, the highest Z reported to generate a single droplet. This was all done with a pneumatic printhead, which operates on the millisecond timescale. We plan to use the ElemX to understand shorter timescale droplet breakup, as it can create droplets on the order of 100 microseconds. Next slide. So high-speed videography is the gold standard in droplet breakup analysis. However, the high data throughput it demands makes it less practical to provide real-time jetting feedback during a build. Think of doing real-time image processing on gigabits of data per second. In response, we have developed a microwave diagnostic that uses an open waveguide to monitor the characteristics of the liquid metal droplets, as shown in the top left and bottom left figures. This method allows for a diagnostic that has a small spatial profile that enables real-time process control feedback with low data throughput requirements. Think kilobits per second versus gigabits per second. We can quickly map the reflected wave signatures to droplet characteristics like size in the top right figure, shape, velocity, trajectory, and temperature by using trained classification algorithms like on the bottom right and machine learning. The takeaway is this will provide more consistent build quality and reduce machine downtime. For example, if droplet generation is out of spec, for example, satellites are being created, then process parameters are automatically changed on the fly to bring generation within spec. Now I'll hand it back over to Kellen to talk about MHD jetting at Livermore.
Yeah, thank you, Nick. Can you hear me okay?
Yep.
Great. Yeah, so the LMX came into operation here around November, and obviously the research that our group has been doing has been pneumatic based. So having this magneto-hydrodynamic jetting technique is a huge of huge interest, just because we're jetting at frequencies that are an order of magnitude faster than the pneumatic technique. So from a science perspective, we have a lot of interest in understanding, you know, some of the effects of, you know, frequency, you know, droplet temperature, and you know, a lot of the other parameters on, you know, part quality, and sort of, you know, looking all the way from, you know, the droplet down to the build plate, you know, single tracks, into actual full parts. And so that's kind of the sciencey, you know, side of it. You know, you heard Tim talk a little bit about, you know, prototyping and, you know, you know, replacement components. So you're seeing on the left there an aluminum cover we had made for a kind of specific experiment we were doing, where basically, you know, printing out a, you know, a plastic part just wasn't going to cut it, because we were going to, you know, be at, you know, elevated temperatures. And so the LMX is great for kind of prototyping parts that plastic just don't really, you know, plastic and you know, polymers don't really fit the need for. And this, like, you know, kind of shows a little bit about, you know, some of the modeling our colleague Victor is working on, and that was part of his thesis, was, you know, looking at sort of ejection. Not sure if some of the videos can play here, but kind of looking all the way from, you know, sort of the droplet ejection to how it's, you know, coalescing on the build plate, and these are things we're really interested in. You know, the fact that you know, the LMX, you know, kind of comes with a slicer that, you know, you can look at, you know, different you know, real, like, building parameters, you know, such as hatching strategy, and complex geometries that, you know, in sort of our bespoke lab setups, we don't have the ability easily necessarily to do. And so yeah, moving forward, we're definitely, you know, looking at, you know, some of these aspects, and you know, hoping to you know, publish good papers, and work directly with Xerox on some projects that we're really excited about. So with that, I'll hand it back to Tim or the America Makes team. Thanks for listening.
Thank you, guys. Jason, thank you, Nick. We appreciate it. Oh,
Thank you,
Kelly,
gentlemen.
yep.
I do want to thank everyone for your presentations. And we're going to head now into the Q&A session. I notice we have several questions out there. If you have a question for any of our presenters and you have not already typed it in the Q&A box, please do that now. The first question is, can you review what's typically required for post-processing or parts?
Yeah, happy to do so. So in general, if you recall the video that I showed, the post-processing to get a part in hand is as simple as submerging the hot build plate in the water bath. So that's going to create separation. Put the part in your hand, ready to use in some cases. You know, depends on the application, obviously. Beyond that, it would be you know, very typical things that you would see in conventional manufacturing as well. That's casting or other AM tech as well. So you might do some CNC machining to remove mechanical support structures. It is just a single jetting system. So if overhangs exceed that kind of 45 to 50 degree range, we would the slicer that comes with the printer automatically creates support structures, mechanical support, so they would have to be removed. You know, typical practice is to undersize things like holes to improve accuracy. So you print an undersized hole and then bore that out afterwards. That would be a typical operation as well. And then there might be some surface work as well if that's required in the application. So you do blasting, polishing, or smoothing operations to improve surface finish for fluid flow channels or something like that. So it really just depends on the application. In general, a printed part, especially once heat treated, it's going to behave very much like a traditional cast part. So there's no unique challenges to finishing a part that comes off the LMX printer.
Thank you. The next questions, they're kind of opposing. First part, how well does the technology scale to larger parts? And then the flip side of that is, what is the smallest feature size that can be printed? Say whole size, for example.
Yeah, great question also. Thank you. So in general, we have a design guide or some design guidelines we can share that talk about some of those feature aspects. We typically recommend like wall thicknesses down to 2 or 3 millimeters. We can push beyond that a little bit in certain cases. It really starts to depend on the geometry. We prefer to stay at like a 2 droplet width or thicker, so that ends up being about 1.5 millimeter thick walls or thicker is where we tend to have the most success. 3 millimeters is quite safe. But we realize not all parts fall within that limit. So pushing beyond design guidelines is perfectly acceptable in many applications. And the same with hole sizes and things like that. Down to 3 millimeters is no problem. Even 2 millimeters, when you start to get below that, we do see a little bit more variability. And if you go down to about a millimeter diameter hole, we tend to see those close up quite a bit. The droplet placement isn't quite precise enough, and or just where they come together, the slicer even tends to struggle with creating that feature. So typically, in the 2 to 3 millimeter type feature sizes are about as low as you go. And then as far as scaling up to larger parts, inherently the technology scales quite well. Right now we have one of the overarching limitations of the existing machine is we can print about 2 pounds of material throughput, maybe up to about 3 pounds. And then we have to replace some nozzle components. We get a buildup of dross in the lower pump is what we call it. It's kind of equivalent to an FDM nozzle, if you know how those operate. And just like they build up material over time and clog up, our nozzle starts to get more variable after about that 2 pounds of throughput. So that would require a 20 to 30 minute operation to replace that in between part builds. We have a number of R&D efforts ongoing right now to expand that max part size or max throughput to the 3 to 5 kilogram range, so 3 to 5 times where we're at right now over the next year or two. And then beyond that, we're again continuing to work on different methods, but there's nothing really about the technology from a physics perspective that doesn't scale up well physically. So in the future, we'll definitely be expanding the size envelope for parts.
And when can we expect readiness for nickel-based alloys?
Good question. Right now, as I talked a lot about, we're very focused on the aluminum alloys because they're very well suited to our technology. They have a melt temperature that works well with all the components in our system. As we push up into higher melt temp materials, we've demonstrated internally materials up to melt temps around copper. So that's one of the things we're working on is commercializing that as well. And then as you look at higher temp materials, whether that's nickel-based or ferrous or titanium, things like that, that's definitely a little bit farther out, more than that, beyond that kind of 3 or 4 year range for sure, because that requires some re-engineering of head components. Again, I think there's not physics issues necessarily. It certainly can be done, but there's certainly some material science challenges within the head that we have to address from a development perspective first.
Thanks, Tim. I have a question here for the Lawrence Livermore team. What do you think is the biggest advantage compared to PBF, and what do you think the biggest limitation is?
Yeah, that's a great question. I'll go ahead and take that. Nick and I are actually having kind of a sidebar discussion that goes into that. Me personally, so I came from using powder bed fusion, so I joke with a lot of people that when I came to the lab, the glove boxes were awfully clean compared to anything where you are working with powder. So that is a huge advantage. And if you can, if a company like Xerox and any other startups out there, or maybe could get up to materials that, powder bed, is known for printing, those nickel alloys, and steels and stuff. I think there may be a sort of a direct comparison. Obviously, the resolution though is a challenge right now because we're working with 500 micron drops. So we see kind of like 1 millimeter line thickness, essentially, because your drop, if your build plate temperature is hot enough, it will sort of kind of come down like a pancake versus a spherical drop, and if it wets the surface, of course. So yeah, I think resolution is the biggest challenge, and then the material selection right now. And as Tim said, there's a lot of material science questions, a lot of complicated components in the head that make going up in temp challenging. So yeah, I think that's kind of my take. I don't know if Nick maybe have something to add to that.
Oh, and you hit the head, nail on the head. I mean, if we want to print, powder bed diffusion, you get 50 micron laser spots. And to get that 50 micron resolution, you need a 50 micron droplet, but that's going to really, your throughput's going to be a lot slower. So there are ways around it, but right now, resolution is the biggie.
Thanks, guys.
All right. So I'm going to attempt to close us out here. Do I sound clear, guys?
Wait,
Yep.
Jason, before you do that, Tim, I
Yes.
think you have one other question in your chat. If you could address that, please.
Okay.
Oh, sorry.
It's in the chat.
Yes.
I actually, oh, here. What's the smallest? All I see is the feature size one, but my window won't expand very well here.
If you click on that arrow next to chat.
Yeah, I'm on that. I can't see it. Hold on a sec here. I see the thinnest wall that can be printed, smallest feature, readiness for nickel, and oh, can you talk about metallographic analysis and typical defects? Sure. That might be a good follow-up too. So we've done a fair amount of characterization on microstructure and some of the typical defects that we see, particularly between layers. I'm not sure that I have anything. I don't have anything handy to share on that, but like the as printed grain structure is actually quite a bit finer than that of a casting. And then it becomes, as you go through the solution treatment, it changes somewhat, but still remains somewhat finer. That's just kind of inherent to the process, which is generally considered a benefit. But we have a pretty detailed review of that. We actually have a metallurgy guide as well on our website that I can send out if you want to connect. And that might be a good place to start. I'm not a metallurgist, so I can't speak to some of that in great depth anyway, but we do have some great expertise on the team, and I can always pull them in as well. So thank you for the question.
Thank you. That's all the questions we have at this time. Jason, I'll turn it back to you.
All right. Thank you so much for fielding the Q&A, Lori. So that's going to wrap up today's TRX webinar series. I just want to take this opportunity to once again thank Tim, Nick, and Kellen. That was a great presentation. And then if you have any further questions for the presenters, you can reach out them directly. Do you have an email address you'd like to provide the attendees with?
Yeah, I did share it briefly. I can share my screen again and leave that up for you as well. Let me do that right now.
All right. Yeah, and I'll just keep going.
Looks like I took away my own privilege.
Uh-oh. Lori, you want to give him privilege again real quick? And I'll just move on. So there will be a post-webinar survey going out to all of those who participated. We do really appreciate the time you take to provide America Makes feedback so that we can continue to improve and strengthen the additive community. And as a reminder, that if you think your organization would be interested in sharing on the TRX webinar series, please fill out the form that follows the presentation, or you can reach out to me, Jason Thomas, at jason.thomas@ncdmm.org. All right.
Thank you, everyone. I did put my email in the chat too. You can grab it right there. It's just tim.schniepp@xerox.com. I'm on LinkedIn too, so feel free to connect anywhere and happy to address any questions and maybe better answer that metallurgy question at the end if you're interested in connecting too. So thank you. And really a big thanks to the Lawrence Livermore team. Kellen and Nick, you did a great job. And we appreciate your partnership and your interest in our technology. So thanks.
All right. Well, thank you very much. Thanks again for joining us, and everyone have a great afternoon.
Thank you.